morning, ladies and gentlemen. Ni hao. I'm sure you have recovered your strengths after the coffee break. My name is Enrico Zio. I'm a professor in the chair on system science and the energetic challenge in Central Superlab Paris, and I'm a professor in the energy department of Politecnico di Milano in Italy. And I have the honor to chair this session, the second keynote session, which has two distinguished speakers that will tell us about two key problems that we have heard today: the complexity of systems and of network systems in particular, and then the efforts in research for prognostics and for predicting failures in systems, in components and systems. I will start introducing right away the first keynote speaker, Professor Shlomo Havlin from Bar Ilan University in Israel, who will talk to us about cascading failures in networks of networks. Professor Shlomo Havlin is a very, very well-known and distinguished professor and scientist in the areas of physics, of statistical physics, and in particular the applications to the complexity theory and complex systems. This is not only the only field that he's been working on. He has a Master of Science and a PhD from Bar Ilan University. He is a professor of physics there. He has been the dean of the Faculty of Exact Sciences in the university, and he has been the president of the Israel Physical Society in the past. He has really contributed a lot of fundamental work in statistical physics, and through his work he has opened new areas of investigations and new ways of understanding physics and the physics of systems. Some very interesting work that I had the pleasure to study myself is also on the understanding of anomalous transport in disordered media, discovering long-range coloration in DNA sequences and physiological data. He has demonstrated that many real networks belong to a different universality class because of their heterogeneous topology. He has been awarded a number of prizes, including Weizmann Prize for Exact Science, the A.P. Nicholson Medal for Human Outreach, the Excellence National Center Award in Israel, and the prestigious Humboldt Senior Scientist Award from Germany, and the Landau Prize from Israel. Professor Shlomo Havlin, thank you very much for honoring us with your presence.
One can be electric grid, for example, this network is electric grid, and another one is the one depends on the other. Electricity depends on communication. You need communication for transferring the control to control the power grid, and transportation you need, and you need other services. So it can be many networks, like this four that I present here, but they depend on each other. And the dependency is given by the red links. It means that a node in one network, which is connected by a red link to a node in another network, they depend on each other. It means if one node fails in one network, it causes the failure automatically of the node in the other network. And this concept of dependency actually was not studied before in physics, statistical physics, and we realized that this can change and generalize what we know in one network, we can generalize to network of network. If you don't have dependencies, or if you have in the network of network only one network, we get back the result of one single network. And what is new in network of network is because of the dependencies, failures in one network lead to failures in another network because the nodes depend on each other, and another network and another one, and it can come back to the first network. We call this cascading failure. The failures can go from one network to another, and even come back to the first failure. So we have cascading failures, and this cascading failure can lead to a collapse of the system. If you have enough failures in the beginning, in one of the network, one of them, this cascading leads to collapse of the system. And this is very different from what we know from simple network, where usually you don't have abrupt collapse, you have continuous collapse. If you remove some nodes here, the network becomes smaller and smaller and smaller, but does not collapse because you don't have cascading failure in single network. But let me start from single network and then come back to a network. As I told you, since 2000, we started to understand single network. What is a single network? A network is a structure that contains n nodes and edges. This is the target for a network. We have nodes and edges between them. And we say 2m links because links we count from each node, so it's counted 2 times. Now in mathematics, we call a network graph in mathematics. And why networks are important? Because complex systems can be well described and understood if you use networks. You can take a complex system. The complex system is usually a system which has many components and they have interactions, and we describe it as a network. For example, if you look on the internet, nodes can represent computers, and the links are the cables between them. So you can see this as a network, the internet network, computers, and links. Now, it does not mean that the links are the same. It can be different type of link, different links, different weight of links, different nodes. It can be dynamics also, but in principle, you have nodes and links, and we can learn about the system from the topology of the network. Airline network, for example, nodes represent airports, and links direct flights between airports. So if I have direct flight from Beijing to Tokyo, then this is a link between Beijing and Tokyo. And climate system also we use networks. Nodes represent location, and links similar climate between the locations, and then we can learn a lot about the dynamics and the climate dynamics using networks, because we don't look on a specific area, we look on the interrelation between areas. And this tells us new information that does not exist just if you look at a certain area. Now, we have many successful results by using networks. For example, we know how efficient immunization strategies, how to make a strategy to immunize a population, to immunize computers. Which one to immunize? You cannot immunize everyone, but you want to know which one to immunize in order to stop the disease. And because of knowing the topology, we can learn how to immunize better, identifying key players in the network. We can understand better the robustness of the network to certain type of failures, random failures, specific failures we can understand. We can even understand physiology better by network, because the brain interacts with the heart, and the lung, and all these systems interact. And if we we can see what happens in different diseases. And we can see that some interactions, and these are, the doctors don't measure now interaction, but in future, hopefully, they will measure the interaction, because the interaction between systems, usually now you measure the heart rate, you measure the blood pressure, but you don't see the interaction. We believe that interaction between systems is new. First of all, it's new information, and second, it will lead maybe to better understanding of physiology. Protein network, also interaction. So let me tell you what was the breakthrough in 2000. Why I think 2000 is an important year. And the reason is that before 2000, we had also graph theory. But the graphs that we analyzed were not so suitable, or not suitable to real networks in reality. And the graph that we analyzed was a Poisson distribution, meaning that a node has a certain degree of the node is the number of links per node, was assumed to be always a Poisson. Before 1999, before 2000, you can see all the papers were assuming that the graph is a Poisson type, meaning that a node can have a certain degree, number of links, and the number of links is given from the Poisson function, like a bell-shaped function that you see here. The bell-shape, this one. And this is similar to, we have such network, like the road network in America. You see every city is a node in the network, and it has about 3, 4, 5 roads to other nearby cities. However, only in 1999, which is that before 2000, we realized that networks, many real networks, are not like the road network. For example, if you look on the airline network, we see that it's very different from the network of roads. Why? Because we have also hubs, we have also nodes which have many links, like New York, like Miami, like other places, and the distribution of the number of links per node, is not given by Poisson, but it's more like a power law. Power law can give, power law means a log log to a log log, it's a straight line. It means that you do have a probability to have large degree, high degree nodes, while in Poisson, the decay of the function is very fast, and you cannot have high degree, it goes to zero very fast. Power law goes to zero slower, and that's why you can have also high degree, which characterizes very well, I will show you later, the airline network. And in the same year already, in 1999, it was found that the www network is also not a Poisson, but a power law, which we call scale-free. Scale-free means that you don't have a characteristic degree. If you have a Poisson, there is a characteristic degree, let's say 4 or 5, and there is some deviation. But here you can have all degrees. Of course, you have low degrees, many low degrees, less higher degrees, and less, but they all follow the same law. So this is the www, but in the same year was found also by 3 brothers, computer scientists, Palutzos, 3, the same name, and they found that the internet itself, surprisingly, somehow, is not Poisson, is a power law also. You see, this is their result. The internet means the number of links that the computer has to others do not follow Poisson. And this made the change in our understanding, and this is the airline that was found only in 2006. This paper is studied the airline, and we found the airline is also not, it's a power law with a degree, but not Poisson. So, and this changes completely the behavior of the network. Poisson behaves in one way, and power law, scale-free, behave in another way. And let me just give you 2 examples in the difference between a network which behaves like Poisson, this is the function of Poisson, like a node has typical number, we say typical number of links, typical can be 2, 3, can be 5, but there is no much deviation between the degree, you can see here. But in the scale-free, which is a power law, you can have big deviation. Some nodes have 1 link, like this one, there's only 1 link, but this node has already 5, and this one has already 10. So you can have a broad distribution of degrees, and this changes the universality, the behavior, and the reason is because there is in this sense, we can say that the exponential of the Poisson is like homogeneous, similar to some regularities. Every node has almost the same number of leaves. So this we call homogeneous, because from every node you see the same similar network, you see the similar number of leaves. However, here it's very different. From this node I see only one node, and from this one I see already 5, 6. So there is a big difference in the concept of symmetry. So the symmetry breaks. There is no symmetry between the nodes here, while here you have the symmetry. Of course, it's not exactly the same, but it is a typical number, but here you have a row distribution, no symmetry. And this makes the system of row distribution scale free in a very different universality class. We know always that if you change the topology, dramatically you change the property. Like you go from one dimension to 2 dimensions, the properties are very different. From 2 dimensions to 3 dimensions, we have different properties. The same is when we go from this symmetry to this symmetry, we have new properties completely. And let me give you 2 properties, but there are many different. One property is related to the distance. The question is, what is the distance, the average distance between 2 nodes in the Poisson, in the training network? And the answer was given already in 1960 by ICRSE&PHM, where they found that the distance goes like log n. Log n, if n is the number of nodes, log n is a small number, and that's why it was called small ball. If you have 10 to the 6, then you get log of 10 to the 6 is 6. It means you can go from one node to another by 6 steps. And this, from this comes also the concept of 6 degrees of separation. Because movies and shows and this, it means that everyone in the world is connected to everyone by about 6 steps. You know somebody, you know somebody, you know somebody. In 6 steps you can meet the president of China, now president of the United States. However, this is correct for this network. Mathematically it will show this. However, what happens if you have scale trees? It becomes very different. And what is different? Instead of log n, you have d, the distance, becomes log n. Another logarithmic makes the distance much smaller. Mathematically we can prove it, and the reason you can understand, because of the hubs, they make people closer. All the people that are connected to the hub are only 2 steps from each other. This one is connected to this one by through the hub by 2 steps. So, but this shrinks the wall to make it, we call it ultra small wall. It means our wall is even, because the population is not like our network of people is not like this, is more like this. Some people have many friends, and some people have few friends, many people have few friends, like this one. So the distance is not log n, but log n. It means by 2 steps or 3 steps, you can reach almost everyone. This is the concept of ultra small wall. And this was found only in 2003. But not only this, what is the stability of the networks? Stability means if I start to remove nodes, what happens to the side of the network? So this network has a certain number that you can remove, and you can find the fraction that we still are left, the critical fraction that are left, and the network still survives. It means you have a big component of the network that survives, and PC, it's called PC, it's related to perforation theory. This is a very important concept here. PC is how much is left, how many nodes you don't have. One minus QC is the number of the fraction that you remove, and the network collapses. It's a phase transition. When you remove above this fraction, you remove above QC, the network collapses. The PC was found to be 1 over K average. It means if K average, the degree average is 3, let's say, you take 1 over 3. If you remove 2/3, 1 minus 1 over 3, 2/3 of the nodes, the network will collapse into small pieces. Each one will be very small. If you are above this, still the network is of the order what is left. The big component, what is left is still of the order of n. If you are above PC, if you are below PC, it collapses completely. What happened here in scale 3? PC was found 0, and this is very interesting. Why? This can explain why our system is more. PC 0 means that you need to remove almost all nodes in protein network is scale-free, is powerful. And many systems, and the internet, why it's so robust? One of the questions was in the internet, why if we buy so many antivirus systems, still the viruses can flow in the system and infect. And according to the Erdos training, it should not be done, should not be spread in the system, but this was not understood until we understand that the internet is not Erdos training, but it's carefree. And that's why even if you buy 99% antiviruses, 99% of the people who buy, it will not stop the viruses in the system. And many people are, so now, but what is also interesting, that we can also, in this case, we can predict the size of the component, of the larger component that is left after we remove no fraction of nodes. And this is the size of the component. If we don't, this is P1 means we don't remove anyone. It means that the network is fully connected. P0, P infinite means the fraction of the nodes that can communicate. So here, I don't remove anyone. The fraction of nodes that can communicate, I can send a message from everyone to everyone in this system, everyone connected. Once I start to remove nodes, the system breaks. This is the picture that shows how it breaks. It breaks. There is a giant component, still of the order of this, but there are small clusters which I don't care so much, because they cannot send, this one can send only to this one, this one, and only those can communicate well. So this giant component is the network which is left, and it was solved analytically for Erdos training network, and was found to have this formula. This formula I want you to remember. This formula tells you what will be the number if I have a degree, average degree K, and P is the fraction of nodes that I don't remove, the fraction of nodes that are left. 1 minus P is the one. Then I can predict exactly what will be the giant component, what will be this component for every P, and I can predict PC. This is for ER. For scale-free, as I told you, PC becomes 0. It means all the time, any fraction that you remove from here to here, still you have a giant component. Only when you reach here, you remove everyone from the system, of course, you don't have a giant component. And also we have an analytical formula for this also, to predict what is happening. For the network after attack, after random attack. We can do it also for other type of attacks. And if we know this, we can also learn how to improve systems. For example, here an example, we show that by changing very little the power of green in Europe, you see from green to red, or from red to green, I don't remember, or from here, we can improve dramatically the resilience of the network. Why? Because we see this is the amount that we remove. If I remove 10% of the links randomly here, or the nodes, the power grid node here, then if I don't do anything, the current system, I will be left only with this side, which only 10% will be able to communicate. However, if I improve the system by changing the links, like here, I can change it from 10% to 50%. It means that I can improve, if I know the structure of the network, the topology, I can improve the topology in such a way that random failures will not lead to almost collapse of the system. And this is one example. Another example for that is a group by Beijing, here. How to improve transportation in Beijing using percolation theory, using network analysis. So this is like a part of Beijing, it's central. And this is the velocities in Beijing. The yellow, the green are the best high velocities, the yellow are medium, and the green and the red are the low velocities, the very low velocities in the roads. And if you look, this is a picture that was taken at this date, 1998. Now what do we do here? We use it as a network, and in this network, we can analyze percolation by, if we know the velocity on each road, we can change the velocity, a threshold for the velocity. If I don't care, I don't care about the velocity, and Q is 0, I can have everyone can use the system. In this case, every road, like in this case it was 390 roads, they all are fully connected. Now what I do, I change the velocity, the threshold. I say, those that are below 10 kilometers per hour, I don't consider them. I say they are not functional, so I remove them. In this case, I have less and less all the time, and when my Q is larger, I can find what is the critical velocity above which the system, this network, breaks. So it means if I am here, you see Q.19, all the roads are for me perfect. If I'm below 19, let's say, the fraction here is actually represent velocity in relative velocity. If I'm in 90% of the relative high velocity of this road handle, then I can use the system very well. Everyone is green, means everyone is functional. However, when I ask only, I need only roads which are above 70%, 69% of the maximum velocity, I get only few clusters, people can move only here. And here I find a critical value in a given time, and the critical value is about 38%. If I take 38% of the velocity, I can see that the system breaks, like evaporation, it breaks into 2 or more clusters. It means from this side, Beijing, to this side, I cannot move anymore. And here we can find, this is the critical link, which actually tells you that these are the roads that makes the problem that you cannot go from here to here, because these links are the roads that are below this threshold. And that's why they disconnect the 2 clusters where you can move freely. And by this way, you can identify the bottlenecks. And if you see that these bottlenecks are every day, you say, okay, maybe we try to fix these bottlenecks in order to improve the system, the traffic. And we can also characterize by this QC, the critical percolation threshold, every time of the day. And this critical threshold is very important to characterize the traffic in the city. If the critical threshold is high, it means the function of the city is good. I mean, the traffic is good. However, when I come to rush hour, you see what happens. Instead of going by 50%, 45% of the velocity, I can go only by 15% of the velocity. It means the velocity drops down and then comes back, and then again in the rush hour. So the rush hour makes it. In the weekday, this is the weekdays, the regular weekday. In the weekends, you see the profile is different. So if you have a profile, it tells you the velocity, what is the quality of the traffic, global traffic in the city by using one parameter, you see. Now we come to network of networks. And from single network to net, I told you that in 2000 we realized we have started to understand one network. Now in 2010, I want to tell you a little bit what we understand now when we have a network of networks. Network of networks is represented by this picture, where the nodes in one network depend on nodes in the other network, represented by red links. And of course, cascading failure is not new. It was seen in Japan, many places, but in Japan, even the title of the paper was in the same day, March 14, 2011, Cascading Disaster in Japan. We had the power grid failure, and the transportation system, and the communication system, everything failed. The word cascading failure, it means such systems that failures in this system lead to failure here and here and here. Can we model this? And can we understand this? And this is what I'm going to show you. Now, infrastructure, interdependent infrastructure, this is not new. It was known already, it was given the picture by Rinaldi, an Italian scientist in 2001. He showed that every infrastructure depends on almost all other infrastructure. You see, the electric depends on oil, depends on transportation, depends on natural gas. So you cannot study the electric power like a single network. We must take the interaction, the dependency on other networks. We cannot study transportation without a dependency, because if transportation, the electricity does not work, you know, the subway cannot work, or many things cannot work. The lights cannot work, so everything depends on each other. Now, there is a clear example how dependency led to blackout in Italy in September 28, 2003. Blackout means that all the country did not have light, and not only didn't have electricity, but the radio could not move, the healthcare system, the financial system, communication system, everything. And this was caused by cascading failures. There was a failure, and this was analyzed in this paper. He analyzed this blackout in Italy in this paper, Rosato, engineer from Florence. And he realized that it started with a failure of a power station around Rome, which led to failures of communication system. The SCADA is a communication system that controls the power grid. Controls means then the power grid will send the electricity, very missing, very extra. So, and this failure caused several stations here not to function because they got the electricity from this place of the power station. And if there's no power, there's no communication. But not only this, and this is important. The green points here in the communication system, they were connected to the network through this through this communication system. You can see the green is connected to this one. This green is connected to this one. They got information, the global information in the system, through this node. And this one also was connected to this one. So when this failed, they cannot know what happened to the power grid. They cannot know this green, could not know what happened. So they also failed, stopped to fail. And this caused cascading failure back to the power, because if this does not function, this one, and this one is connected to this one, then the station did not know what to do with the electricity. It stopped working. So this stopped working also. And then they were cascading between the system, and then Italy was broken into two parts, and then they stopped, they could not understand more the electricity, and there was a blackout in all Italy. Now, let me show you what is the difference in the theory between a single network and the network of networks. So in a single network, as I told you before, we have this type of breakdown. If I remove more and more, the system still continuously goes to zero, by a function that we can analyze. However, when we have cascading failures, when we have dependency like in this system, this is not anymore true. When you have dependency, this smooth function of failure, which occurs in a single network, this one and this one, is not anymore true. What happens is, if you have enough failures, like here, from here to here, you remove, in one of the systems, or in all systems, it doesn't matter, what happens, you start to have cascading failures here, cause failure here, and it reaches a point where the cascading are so much that they lead the system from this point down abruptly to this point. And the failure just continue to make other failures, and then the system goes abruptly. So instead of having a continuous, we have an abrupt. And this is a new paradigm that was not considered before. Before it was continuous, but when you have abrupt transition, you are very worried. The system is very risky. You don't know if you are here, you don't know what will happen. It may happen that one node more will cause the cascading and the system will be abrupt. If I am a controller of a power grid, and if I have a single system like this, I'm not so worried. Why? Because if I have less power stations, I will have less customers. But it does not drop to zero. Here, the system drops to zero. It means that nobody will be able to use. And this is what is the abrupt transition, is the one that causes very worried about interdependent systems. If you have interdependent systems, it can cause abrupt. Now, this abrupt, luckily, I want to tell you, is not caused fast. But it takes time. It goes from here to here to here to here to here and back, and can be many times. And the abrupt transition, if I look at this, the time that it takes from here to here to go down, from here to here to go down, I Then there is many steps to back and forth in the system, but very slow, very little damages. And these very little damages go in the plateau here, and later it goes down. This is done in theory and in simulation, and even we can find that the time, the number of iterations that the system goes, the cascading goes like the synthesized to the power of a third to the body. For example, if you have a million components, it will be 100 steps back and forth. But this power depends very much on the system. But this gives us hope. If we have such a plateau, maybe there is a hope that we can stop the plateau. Instead of going down, it will continue here. We have some time to be prepared to stop the cascading between the system here. And this is a theory to explain what happens during the plateau. There is only very few damages, like a tree, like a critical damage. A tree like this, you see, one damage in one system, it's two damages. The branching of the damages here are very small branching. One damage makes one, on the average one or two, one, and that's why it goes very slow till it reaches, and we can explain this and understand this in this paper. It's very well understood what happens in the origin of the plateau. And in order to find, you can also easily find in the plateau and find what is the critical value, how much you have to remove in the system if you don't have a theory, how much you remove in the system will collapse. Let's say I take this complex system, how much to remove to collapse, I can make simulation and find I remove more and more and more. When I reach criticality, the number of iterations, which you call here, goes to infinite, goes very large because of the plateau. And that's how we can estimate what is the critical value of the damage that I make the system, and the system will collapse. Because here you see there are little cascading failures, here little, but only at criticality I have a peak number. This appears only at criticality. I mean, if you simulate it, you will see immediately when you reach criticality in such a system, you will have many cascading failures. If you are not criticality, failure will, but not too many. But at criticality it goes very slowly, and that's why the number of cascades is very high. The number of times it goes back and forth. And this is also very important. Now, I told you about coupled system, and now the question is how much dependency I put as I see this phenomenon. If I don't put dependency, of course, I will not have the phenomenon, the breakdown. But how much dependency? And this we can answer also theoretically, analytically. How much dependency? First of all, we take here two networks. One network is heterogeneous, another one is two dependency. And we see here that if I put 80% dependencies, 80% means 80% of the nodes here depend on me, and 80% here depend on this. The red links represent dependency. It can be both directions or one direction. Then I see the abrupt transition. But if I put 10% dependencies, it's almost not dependent enough, and then I see a smooth transition. First order means in physics abrupt, and second order means smooth transition. This means the first derivative diverge, and here the second derivative diverge. That's why it's called first and second. So we have now a new phenomenon, a new finding of critical dependency. If I put less dependencies, I will have a smooth transition. If I put more than critical, I have abrupt transition. Abrupt means you have cascading enough and the system goes. And we can change if we know the system, we could now, after the fact, we could change a little bit the interaction between the two systems, common communication and the power grid, and instead of having all Italy, half of Italy disconnected, we could have only two Sicilia maybe disconnected. If you change, because if we know now this theory, we can understand it better. But now let me show you how to generalize the single network to many networks. And this is the last, I think, series that I want to show you. Now, you remember I told you that if I have a single network like this, and I remove nodes, single network, the giant component, the network, goes down smoothly the number of people that can communicate in the network goes down till a critical value goes to 0. This is for single network. Now what happens if I take network of networks? I take here, this is a network, this one is a network, this one is a network, and the links here between the networks represent dependency. I put here dependency links between this one and this one, between this one and this one. And the same I do here, and the same I do here. And I take 5 networks. Now I want to make the solution that we find that was found by Elder Schlein 60 years ago for this function, the size of the component, the size of the network. I want to do it for 5 or for any number n. And surprisingly, what we find is that this formula becomes now this formula. You see, this formula does not have anything, a power here, but this formula has a small power, a number of power, which is n. What is n? N is the number of networks that are dependent on each other, like this, or like this, like this, 5. If I have n5 like this, I put in 5. And what I see when I have n2, see, instead of having a smooth transition, and I solve this is a consistent equation, I have instead, for n1, I have a smooth transition. This is mathematically, you can prove it easily. I solve P0. It's a self-consistent equation for P0. And I get smooth. But when I take already N2, it's not anymore smooth. It comes to a point where, boom, it goes down to 0 abruptly. The solution of P is infinite here, when N is 2, is not smooth, not continuous abruptly. And for N5, it goes abruptly. So we can find PC here, PC here. And this is very interesting because it shows that what we did 60 years in single networks is only a specific case of the general case of n networks. N means I have n interdependent networks. It means that this is a generalization of single network. And we can see that in the formula, of course, Elder Schlein, when he did it in 1960, it studied only single one. But when we do it today, we know that this one that appears here did not appear because one we don't put as an exponent, but it's supposed to be n. N is actually the real solution. When n is 1, we get this solution. Now we can also find another point which is very important, is the critical dependency between how much dependency I have to put. And here is another example of generalization of network. But if every network depends on m networks. This is a network, but it depends on m network. But not only this, we have another parameter which is q. Q, how much a network depends on network. 10% q can be between 0 and 1. If it's 1, every node depends on every node. If it's 0, nobody depends. If it's 0.1, it means 10% of this network depends on this, and 10% of this depends on this, and on this. Every link is dependency. And now I have a formula which is also not so complicated. It tells us how the giant component behaves, how the network behaves as a function of P. P means how many I don't remove from this network, how many are left. M is the number of networks that the network depends on. M is here, M is 3. K is the average degree of this network. Because of symmetry, all the networks are the same to get simple solution, but you can do it in general. And Q is the new parameter that tells you out what is the fraction of nodes here depends on it. And you get this solution. And this solution is also very interesting. Why? Because when I put here M0 means that a network does not depend on other networks. And I put here M0, I get here, this becomes 1, all this term, this 2 to the n becomes 1, and I get back the single network solution, this one. So M0 means no dependency in the network. I get back. I can put Q equals 0. And I also get, if I put Q equals 0, you see here I get 0, I get 0, I get 0, and I get 1 plus 1 to the power n, 2 to the power n, which cancels with this to the power n, and I get again the single network solution. It means that I can see it's a natural generalization of the single network result that was known 60 years we studied this extensively. But what is new here is QC. That tells you for each M and K, what is the critical value of dependency that you can put in the system below this, and the system will be smooth transition, and above this dependency it will be a abrupt transition. And this is very important for us for reliability also. If I have a system which goes smoothly, I'm more safe, I'm more quiet. But if the system goes abruptly, I'm very bored. So this QC can be found and understood. So let me go to the summary. So I showed you statistical physics approach for network of interdependent network, where we see cascade failures. You have to remember a new paradigm, abrupt collapse, compared to continuous in single networks. If I have a single network, I have a continuous. This is a single network, I have a continuous. But if I have two network dependence, or 4 or 5 networks, I have abrupt collapse. Now I showed you that we generalized the single network result to any interdependent network. 50 years of collapse theory is only a limited case of single network, and when we do interactive network, we see much richer phenomena. This is like in physics, where we had, under 20 years ago, we studied only particles which do not interact, like gases, but when we have interaction between particles, we see much richer phenomena. We can see liquid, we can see solid. The same happens also here. When you have interaction, you see completely new phenomena that did not appear in the procedure. I told you about critical dependency. This is good. If we can make the system that it will be dependency below QC, we are more relaxed, but only above QC it will be abrupt. So we have a new parameter. Cascading failure as a plateau, this is also very important. This plateau, how it drops, it does not drop dramatically, but through very slow process of cascading, very few damages. And only few damages it goes here, and that's why this is a challenge for us to solve the problem. Now, so we have a plateau. Now, I did not discuss the question which appears in this paper. What happens if you have recovery? Because you can also go and fix some systems. I spoke only about failures. What is the rate of fixing system you need in order that the system will not collapse? So this is written in this paper, example 2014. What will be the rate, critical rate that you need to fix in order, and which one to fix in order to the system will be functioning? I did not tell you anything about spatial constraints. I spoke about networks which are just random network result or not in space, but when they are in space, they're much different, more similar phenomena, but much more risky. And this appears in this paper. In this paper, you can see space. And the last point is localized attack. When we have a system in space, you have a new type of attack that can make much more damage. You make a localized attack above a certain value, and this can spread in the system and can break the whole system of systems in a very small type of attack. And I want to thank you very much for listening. I hope I gave you some new ideas. Thank you.
Thank you very much, Professor. Thank you. Thank you very much. This is an illustration of the analysis of very complex systems and systems of systems, and in fact the reliability of a product that we learned also in the earlier lectures, also by Professor Michael Pack, is the result of a network of contributions of parts that must all be reliable and all at the quality to make it reliable. We continue with multi-component systems, and we're going to look at how they fail and how we can monitor their condition in order to predict the remaining useful life. And in fact, for this, we invite Professor Jianjun Shi to talk to us about the new advancements on data fusion research and prognostics. Professor Shi is Professor and Chair of Milton Stewart School of Industrial and System Engineering at Georgia Institute of Technology, Georgia Tech in the USA. Got his Master of Science in Beijing Institute of Technology, then got in electrical engineering, then got a PhD in mechanical engineering in Michigan, the University of Michigan, where he actually was a professor for several years before moving to the Georgia Tech Institute. He has produced almost 30 PhD graduates, which have gone on to very successful careers in academics and industry. He has published one book and more than 150 papers with a very large number of citations. In fact, he has been a pioneer in the areas that he has been working on. He has a very large number of awards, a very large number of recognitions in various academies and committees. He's certainly one of the most active persons in this field. And if I read the whole curriculum, just like with Professor Havlin, I would probably take all the time of the presentation. So please, Professor Shi, you're welcome very much. Thank you very much.
Okay, thank you for the introduction. Right now, I need to speed up because for the time for lunch. So what I try to do is instead of follow all the slides, I try to tell some stories of my research for each topic. And what I like to do is talk about each problem. What is the motivation? Why we want to study this? Why we really say what we have done to solve this problem, and hopefully more people can work on this kind of problem. And I will skip the mathematical details and also our results. And use Chinese, we say 抛砖引玉. In English, I don't know if you will write translation. Zoom try to get with hope, get straight. So I talked some research on a new advancement of data fusion research, basically some 4 new topics we have been done related to prognostics. So in this talk, I will first talk about the framework, what's prognostics, and then some whole topics with different motivation, different problem formulation, and then give a summary. So in this talk, we're talking about prognostics. Basically, is try to use in-situ sensing to predict the remaining life of a system. And here we emphasize a multi-component system because almost all systems need multiple components work together to make system function. And also, due to complexity of the system, there are multiple sensors usually used to monitor some kind of system. So there is the need for data fusion, basically different types of data. How can we combine the information together to get more reliable and more precise prediction on the remaining life of the problem? So basically, the general framework for prognostics is shown here. We need the response of dt as remaining life, and there are 2 key parameters. One is the constant parameter, one is the stochastic parameter. And then we try to use in-situ sensing to predict, to update the parameters and predict remaining life. So here you can see as time moving forward, we have this. So as time moves forward, we have this remaining life up to this point, and based on here, we can predict what's the remaining life distribution like this. And as time moves forward, we can have a better, more information and more precise remaining life prediction. So in Chinese, we say 走着瞧. So English basically we continue to collect information and update the estimation. So under this framework, we talk about 4 topics. I will not repeat this one. I talk about each one, say what's location, why we study this one, why is this topic important. And also I'd like to say the results I present based on our work is quite initial. So lots of work needs to be done to make this better. The first work is simultaneous signal separation and prognostics of multi-component system. So in by the way, all these 4 topics either published or the paper has been accepted. So if you're interested, you can send me an email. I can give you the paper for the ones not published yet. So what problem we try to study? 10 days ago, I was in Highway Research Institute in Beijing, and talking about last week, not 10 days, last week. So basically, they have problems there. How to monitor the track suspension, like each track, there are 4 wheels system, there are 4 suspension systems. And then they can have sensors put on the track, and like here, they can put sensors here, and for each track they have different bearing, different suspension system. And the problem is like this: all these four systems, the seven systems, they have the same components, same if something wrong with the sensor, you measure not individual components, individual subsystems data, but a combination effect of all these four systems. So you want to know from that kind of sensing information, can we get the information of each individual bearing or each suspension and see which one is has problems and how to predict remaining life of this one. I think this particular topic for highway is open issue to try to study. Then I thought this paper they seems very interested. So the objective is using this sensing information, the combined information, and then try to isolate this one into individual subsystems. And the way we formulate a problem like this, let's give this review. So you can see here, this XT here is the sensing information we got. And STK here is the original source of degradation of the system. And AK, it matrix A here is a mix of how we combine this individual separate sensing information and show up in the combined signal, ET the noise. So with this formulation, we can take digital Fourier transform on both sides. And then we only count the real part of this equation, and then take the incremental, we can get the bottom one. So we can get this one. So with this, here is more efficient. So with this formulation here, this one is sensing information, this one is the original signal we want to estimate. And then we use independent components analysis to estimate the mixing matrix A as well as the independent signal. So we use ICA. Using ICA can accomplish this objective, however, there is a limitation. Using ICA, we cannot find the magnitude of the components. So because of this one, we need another proposed. The energy recovery algorithm, basically, we assume the system is stationary for a while and then start degrading. So during the stationary, we try to find the estimation, what's the magnitude of this power. So with this idea, we can get the sensing signal and then the degradation rate of this one to be estimated. And then we can find the posterior distribution of this remaining life. And then we can get this update continuously. So this is a case study. Basically, we say with a different sensing signal, we have different original source of variation. So original source of sensing signal, the combination. By using this signal, we can estimate the missing matrix and also this signal try to do a minimum prediction. And we study the property basically saying for this original signal, the noise level is not critical. However, if the original source of the degradation of interactions have dependency, and then the estimation becomes a problem. So this first topic we talk about. The second topic is residual life prediction of multi-stage manufacturing process with the interaction between tool and product quality degradation. And this paper accepted but not published here. So this is also motivated by a real problem. About 10 years ago, close to 10 years ago, Chrysler has a new body shop in Toledo. So before they start the new body shop, they hired the consultant, they do simulation of IE based on the reliability, try to predict what's the machine life and how often you need to do maintenance. And during this time, during this simulation, they said, okay, the result is 3.5 technicians are required to maintain the flow of the body shop. So after they run the production, they found out they need 7 technicians, work 3 shifts, still cannot maintain the production. So in other words, the software simulation design was not accurate for the maintainability maintenance requirements. So they asked me, say, jam, maybe it come here, why did it happen? So what was, we spent a lot of time in the lab trying to say what's downtime, do the analysis, and we found one important component missing in the simulation and also in academic research. The thing is quality and reliability interactions. So you can see the example of, on the left, this is a drilling process. You can understand like this. So if I have a part coming in, the part material is not consistent, and I try to drill a hole. So not consistent is quality problem. And then I try to drill a hole like this. So if the drill hole not consistent, drill wear out, will be accelerated. So not consistent because of not consistent material. If you drill wear out, the hole should be flat, flat surface vertical. However, drill has a problem, the surface will be rough and not in the regular shape. Because of this one, you go to the next process, packing. So you make a thread on this. So because the hole quality is not good, the thread will wear out much faster. So in this motivation example, you can see the quality will impact on tooling degradation. The tooling degradation will further impact the quality. When you have a multi-stage process, there is an interaction between tooling quality, tooling reliability, parts quality go to the next station, further impact on tooling reliability. There's some kind of interaction. However, in the literature or in the software, they do not consider such interaction. They only consider the tooling wear out and the reliability issues, not consider interaction of quality reliability. And this is motivated by such example. I will skip the second motivation. Basically, in any multi-stage manufacturing, you can see some kind of a QR chain effects. So, for that kind of problem, how we formalize the problem? Say, we say S is sensing variable. No, S is number of tools, and Y is sensing data. So basically, we say the sensing data of poly. So you can see the sensing data is a function of tool burn out. So there's one interaction with the function. And also another aspect, we say the tooling degradation is impact on this degradation coefficients. And further, this is the key. The degradation coefficients is impact by the quality with the natural one and also quality YK. You can see YK over there. So because of this one, we combine this. We can see the tooling degradation is a function of quality, and combine this, we can get this measurement, quality measurement Y is a function of this. So after I formulate this one, the rest will be similar as before. We use this one as measure information and monitor the degradation. So this is, I try to speed up so we can go to lunch. So this is a second example. You see the motivation. Both basically want the quality reliability chain and for that kind of problem. And we study using our technique to predict the remaining life versus a result, considering the quality reliability, our result provides better performance. So this QR chain. The third topic is controlling the residual life distribution of power multi-component system through workload adjustment. This was also motivated by a real problem, and this problem comes from Ford Windsor engine plant, Ford Motor engine plant. In their plant, they have that kind of layout. You can see this one, in fact, over there, they have 7 identical machines, the same machine. Here, the country come here. So they move the parts to this one, and these machines do the same job. So the current, before we work on with that, the process is they move the parts to this work cell, 7 machines. They jump these parts to the first one available machine, and then the machine will do the job, and then go to the next station. Also, they have like 6, 7 same machines doing the same job. So basically, multiple machines, there are several advantages. One is to make sure the throughput is good. Another one machine is broken, maintenance, they still maintain the production line. And during the design, they have an actual capacity. This is in other words, if one machine here does not work, the system still can flow into production. And Ford is very proud of that kind of process in ASME magazine. he introduced this concept. However, what is the problem? What's the nightmare for them, for this plan? The nightmare is if there are 7 machines, if 2 machines, or sometimes 3 machines broken in the same cell, and then that's big trouble for the overall production. There are like 24 different cells. So, and also without control the degradation of machine maintenance, and let them randomly say if something broken, they try to fix it. There are such problems for the maintenance people. Sometimes they work overtime, sometimes they have nothing to work on. So that's the problem they try to do. So they asked us, how can we make smooth production and make the maintenance people working on continuous working flow, working schedule? So if we want to do this, we need to control the degradation of the machine and control the machine cycle time. This is the motivation to try to study this. And how we do this is, so basically we think many people work on the research on prognostics based on data, make remaining life prediction. But how to control the degradation rate and impact on remaining life? This one is something new. And after we did this one, we found some other applications. If we can control the degradation, that is kind of very desirable. Discuss this more later. So this is how we do it. We assume there are 9 different components, each has a workload, workload, and then workload with a given certain rate, depending on the capacity, and the overall throughput is each individual throughput summation of this. So after this one, we have the relationship between the degradation and the Rm is the instantaneous degradation rate. And also we say the degradation rate is related with the workload, UM workload. So it's in other words, it's also with common sense. You let them work more, work harder, the degradation faster. That's the basic concept. So this is the parameters, is degradation coefficients. And by combining this one, we have the sensing signal is workload information, and then we can formalize this. And after this, we can get the mean, or thorough mean, and distribution is function of the workload. In other words, we can change the workload and impact on the degradation rate. And then we formalize the optimization problem. So basically, this one shows the overall degradation rate is smaller. That's the one objective. There are different constraints. So these 2 blocks are important idea. One is we assign higher workload to components with worse health status. In other words, there are several machines may be broken, and we want the almost broken one work harder and then let it broken. That's one constraint. Another one is saying we want this equation tell us we do not want 2 machines broken at the same time. So this is another constraint we solve the optimization. And based on that kind of schedule, we can get the better result. And here is a simulation shows even repair time. Repair time is 1 day, 3 days, 5 days. It's a different time. And so this one is random assigned the machine to different one, which is the current practice. This number 3 is our proposed one. So from this result, you can see the 2 benchmark and our proposed one with the repair time is very short. The performance is comparable. This makes sense because once broken, you can quickly fix, that's no big deal. However, if the repair time is longer, 5 days, using our method to purposely partition the broken time, we can have a much lower throughput loss compared with the current practice, which is the first one. So this is a different strategy. So that's for the third topic. So the last topic is also a data fusion thing, a data level fusion. model for developing composite health index for diabetes modeling and prognostics. This one is this data set, public data set. I think many of you probably studied this one. The NASA engine data. They have like 30-some sensing signal to monitor this engine performance when these are broken, not broken, and the problem here, and also almost all prognostic problem is there are many sensors monitor certain figure. Always some sensor figure is more close related to this particular fault. Some sensors, the less related or not relationship. So there the first is a sensor selection. Which sensor should be included? That's one thing. Another thing is over time, each sensor generates a trajectory or profile data. How to combine those different sensor data together to become one index. And then this index should have a better performance, which can lead into better prognostics. And this is the objective. And how we accomplish this one is saying, in order to have a good composite index, this composite index should have two essential properties. The first one is this data train, the property one, saying that data should have a monotonic, basically monotonic data, that's one. The second one saying for different individual sensor, they should have less variability for the threshold. So if we can satisfy these two properties, that kind of a data index is a better index. So, I mean, in order to do this, we formulate an optimization problem. Sorry, I skipped this 2 slides. Basically, we formulate this optimization. And in this optimization, the W here, W is vector used as weighting coefficients to each individual sensing data. And so this is a summation, the total weight amount on the variation of monotonicity of property 1. So this summation emphasizes the property 1 of this. And then we have these components basically emphasize the property 2, to realize property 2 of this. By solving this optimization problem, these are two parameters to emphasize monotonicity and also the variability of this. So this is a data fusion that tries to solve this optimization problem. And if you're familiar with the data mining on the automatic machine better, there's a similarity between these two. In fact, we motivate by this one to develop this result. One thing we say, data level fusion, different from many people doing is you have data, you get a feature. After you get a feature, how to combine different features. So that is another way of doing this. So what we try to do is we get data aggregation, data pre-processing, and then in this stage, we do the data fusion, combine different sensors together, which is different from what many people do in the feature, extract features, and then do the sensor fusion. After we get this data fusion become one index, we can still work on the feature extraction and so on. So you can see this is the original sensing signal. This one is the composite index, which is much less variability and more consistent degradation. And using our approach, we reduce modeling error and significantly, and reduce variation in the threshold, significantly. And the last one is most important. We benchmark other people did. We can improve by 38%, which is quite significant. I need to say this work has been published is for single fault, single failure. In this data set, public data set, they also have multiple operation conditions. In multiple operation conditions, how can we do the data fusion for complex composite index? It's a very challenging topic. We get some results, but no paper yet. Okay, this is my last slide. We want to say data fusion for prognostics is an emerging interdisciplinary research. It's very important. And I discussed some topics what we have done. So I hope people can get motivation when we work on this one. And if you're interested, send me an email or send me the paper, we can discuss more. Much more work needs to be done in this area. Thank you.
Thank you very much also for accelerating your presentation. I predict that the remaining useful time for the lunch will be extended a little bit, I hope. Thanks to the keynote speakers for the very interesting presentation. Thanks to all of you for participating. And we will see you at the next keynote speaker after lunch.